The two Voyager spacecraft, launched more than 4 decades ago, continue to broaden our horizons. After flying past the giant planets in the late 1970s and early 1980s, Voyagers 1 and 2 have passed well beyond their planetary targets, with Voyager 1 more than 5 times further out than Neptune, and Voyager 2 not far behind. Over the last decade, both spacecraft have entered the interstellar medium, the tenuous material that fills the vast space between the stars. The spacecraft continues to make new discoveries there. The strength and direction of the interstellar magnetic field have surprised researchers, and the new data have even fueled debate about the geometry and activity of the heliosphere, which is the Sun's magnetic domain. Is this heliosphere, as long assumed, the shape of a comet, or is it more spherical? Is it more stable, or does it expand and contract as sunspots wax and wane? The spacecraft has provided some intriguing hints. Voyager was not the first spacecraft to reach the nearest of the giant planets. Pioneers 10 and 11 took that honor. On the other hand, the Voyagers were more sophisticated than the Pioneers and made many unexpected discoveries. Voyager 1 took a shorter path than Voyager 2 and arrived at Jupiter first in 1979, discovering erupting volcanoes on the planet's colorful moon Io. Voyager 1 then flew by Saturn in 1980, observing intricate details in the planet's rings and discovering the first nitrogen atmosphere beyond Earth around the moon Titan. Voyager 2 took the scenic route, visiting Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. Voyager 2 observed geysers on Neptune's large moon Triton and provided spectacular views of the green and blue planets. The spacecraft then began its journey into interstellar space. As defined by astronomers, this interstellar medium begins where the solar wind, the outflow of charged particles from the sun, ends. This ionized gas or plasma acts like a pebble in a stream, pressing against the cooler, denser interstellar plasma flowing around it. The cavity created by the sun is known as the heliosphere, and its edge is known as the heliopause, just as the top of the Earth's troposphere is known as the tropopause. Voyager researcher Don Gurnett of the University of Iowa in Iowa City said that we really didn't know how far out the heliopause was when Voyager was launched. Some speculated that the heliopause could be as close as Jupiter, which is only 5 times further from the Sun than Earth, and estimates of the distance to the heliopause increased as the spacecraft accelerated outward. It was not at Jupiter, Saturn, Uranus, or Neptune, and surprisingly, no one knew when or where the Voyager spacecraft would enter interstellar space. Gurnett claimed shortly after the Neptune encounter that Voyager had seen signs of heliopause in the distance. Both Voyagers began detecting strong radio waves at frequencies ranging from 2 to 3 kHz. Gurnett and his colleagues attributed the radio waves to 6 large flares that erupted on the Sun over a year ago. According to researchers, plasma ejected during the flares eventually hit the heliopause, causing electrons to oscillate and emit radio waves. The oscillation frequency is proportional to the square root of the plasma's electron density, and the radio waves' observed frequency implied a density similar to that expected from the interstellar medium. The local interstellar medium is much denser than the outer heliosphere, despite being so tenuous that it would pass for a perfect vacuum on Earth. Furthermore, knowing the approximate speed of the outbound solar material and the time it took to hit the boundary revealed the distance of the heliopause from the Sun, between 116 and 177 astronomical units, where 1 astronomical unit is the distance between the Sun and the Earth. Such radio waves had never been seen before, and many researchers question Gurnett's explanation for the signals. For another thing, his measurement indicated that the heliopause was depressingly far away. In comparison, Neptune is only 30 astronomical units from the Sun, and Pluto is approximately 40 astronomical units from the Sun on average. On August 25, 2012, Voyager 1 passed through the heliopause at 121.6 astronomical units, roughly 4 times Neptune's distance and exactly in line with Gurnett's prediction 2 decades earlier. However, the passage was so contentious that NASA did not announce the achievement for another 13 months. Nonetheless, Voyager 1 detected some signs that it had crossed the heliopause. High-energy particles from the Sun vanished, implying that the rest of the solar wind had also vanished. And in addition, cosmic rays from outside the solar system, which the heliosphere partially blocks, became more intense after Voyager's passage. Many researchers were not convinced by these signs alone. There were 2 issues. First, Voyager 1's plasma instrument had failed, making it impossible to record the increase in particle density as the spacecraft exited the heliosphere and entered interstellar space. Second, the magnetic field beyond the heliosphere was supposed to point in a different direction, but did not. According to scientists, nature just doesn't read the theorists' papers and doesn't realize it was supposed to change the magnetic field direction. It's still unknown why the magnetic field outside the heliosphere aligns with that inside. The Sun contributed to Voyager's success. Solar storms had erupted earlier in 2012. The following year, they shocked the plasma through which Voyager 1 was traveling, causing electrons to oscillate and emit radio waves that the spacecraft detected. Because of the frequency of those radio waves, Voyager had entered a much denser domain. As a result, Voyager 1 became the first spacecraft to reach the interstellar medium. Contrary to popular belief, the craft had not left the solar system. A trillion icy bodies orbit the Sun, far beyond Neptune and Pluto's orbits. Now and then, one collides with the Sun, revealing a new comet in the sky. The most distant icy objects are probably 1 to 2 light years away, or 63,000 to 126,000 astronomical units. To give you a clear estimation, someone walking 3 miles west from the center of the continental United States has gotten closer to the Pacific Ocean than Voyager has gotten to the solar system's edge. Voyager 2 also passed through the heliopause on November 5, 2018. This time the passage was not contentious. The spacecraft's plasma instrument was operational and detected the increase in particle density as protons, electrons, and other charged particles collided with it. It also measured the temperature, which was between 30,000 and 50,000 Kelvin, much hotter than the local interstellar medium, most likely due to plasma compression as it entered the heliosphere. And just like Voyager 1, the spacecraft observed a decrease in the solar wind and an increase in cosmic rays outside the solar system. Still, the magnetic field failed to change direction, indicating that the result 6 years earlier was not a fluke. The magnetic field is so strong that it changes the heliosphere's shape. According to popular belief, it's shaped like a comet with a nose and a long tail. The nose points in the direction the solar system travels through the interstellar medium, while the tail points in the opposite direction. However, because the interstellar magnetic field is so strong, magnetic pressure, which is proportional to the square of the field's strength, squeezes and rounds the heliosphere. Whatever the exact shape of the heliosphere is, Voyagers 1 and 2 continue to dart away from it. Voyager 1 will be 155 astronomical units from the Sun by the end of the year. The signals from the spacecraft will take more than 21 hours to reach us because they travel at the speed of light. Voyager 2 will be 129 astronomical units away and pass the silent Pioneer 10 this year, in 2023, to become the second farthest spacecraft ever. The two Voyagers are racing away in opposite directions, further apart than either is from Earth. They're still sending data about interstellar space. Both can detect radio waves generated when solar eruptions cause electrons in the interstellar medium to oscillate, allowing them to measure electron density. These eruptions should become more common as the sunspot cycle reaches its peak around 2025. Current measurements show that the interstellar density has risen further from its pre-heliopause level, but no one knows what will happen next.